Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Jeroen Famaey. Jeroen is a research professor associated with the University of Antwerp and IEEE Belgium. He received his master's degree in computer science from Ghent University in 2007 and a PhD degree in computer science engineering from the same university in 2012. This year, he was appointed as an associate professor at the University of Antwerp. He currently leads a team of researchers focusing on the modeling and optimization of wireless networks. Today, he will tell us about wireless interactive VR using millimeter wave communications. Jeroen, the floor is yours.
Thank you very much for the introduction. So my name is indeed Professor Jeroen Famaey. And this presentation was also created with input from two of my students, Jacob Struijen and Philip Lemich. So I'd also like to thank them for their input. And as mentioned, my talk will be about wireless interactive extended reality using millimeter wave communications. And let's start by talking about extended reality. Extended reality is a name that is used to encompass several things such as virtual reality, augmented reality, and mixed reality. And it started as an idea in science fiction. On the left, for example, you can see a hologram in the original Star Wars movie from the 1970s. In this movie, these holograms were used to transfer messages. On the right, you can see a picture from a more recent movie called Ready Player One by Steven Spielberg. And in this movie, there was a grim picture of the future painted where people actually fled into virtual reality. So everyone lived in a virtual world. People put on VR glass, wore haptic gloves, and spent their days in the virtual rather than the real world. But virtual reality and extended reality in general is no longer just science fiction. At the moment, it's reality, and there are many different applications that already use VR or XR. For example, in the entertainment industry, there are a lot of video games for virtual reality headsets available. But also in industrial setting, for example, several companies have developed VR training simulations for industrial applications because it's more safe, cheaper to train with heavy machinery than in virtual reality than in real life. Other applications are remote participation and control, for example, remotely controlling drones or robots, or even medical devices. So these are some examples of virtual or augmented reality applications. And to show you why virtual reality is a very hot topic, I included here a picture from Facebook. And recently they announced that they would focus their efforts in the future on the so-called metaverse. And the metaverse actually comes from science fiction in the 90s. It was coined by a writer, Neil Stephenson. And the metaverse is basically a network of always-on immersive virtual environments in which people can interact with each other and digital objects while operating a virtual representation of themselves. As you can see here in the picture, these virtual representations are also called avatars. You can basically think of it as a VR version of the World Wide Web or the WWW. And it can be used for entertainment, but also for having online meetings, work-related meetings, for social interactions, and so on. And actually yesterday, CEO of Facebook, Mark Zuckerberg, even said that Facebook would change its name to Meta as a link to the metaverse. But if you've used virtual reality headsets, you may have noticed that current headsets that are available on the market are quite bulky and usually connected via a wire. This wire is actually used to connect the headset to a computer, and then the computer renders the images and transmits them over this wire to the headset for display. Obviously, having a wire connected to your head is not very handy, as you can see in these short videos where people are suffering because of this wired connection. You're immersed in the virtual world, you forget you are connected with a wire, you walk around, and then you fall or the headset is pulled off your head. So it's not very good for immersion and mobility. The current alternative on the market is to have the processing on board on the headset. So instead of connecting via wire to the computer, you have a small computer embedded in your headset. For example, the Oculus Quest, which you see here on the left, makes use of that approach. But obviously, this small computer embedded into the headset is not so powerful and therefore cannot render very high definition images. An alternative approach is to have a wire connected to a backpack, and then the backpack is actually a computer you carry around. However, these computers are quite heavy. They make a lot of noise, generate a lot of heat. So also here, it's not the perfect solution and not really immersive. And that brings us to the topic of my talk, which is to get rid of this wired connection or this onboard processing. And instead, we want to wirelessly connect your extended reality headset to the backend cloud or edge data center. So here you see the overall vision. You have your VR or XR users wearing a headset, and this headset connects wirelessly to a wireless radio access network. In turn, this radio access network is connected to an edge cloud server or even a cloud data center. The processing of all your content and storage of your content is then done either in the edge cloud or in the cloud. And the rendered data that must be displayed or the audio or the haptic feedback is then transmitted back to the users. This also allows users in physically remote locations to interact with each other, which is also part of this metaverse vision. And you can walk around freely without a wire tethering you to a computer. There's actually a lot of research that's being done on this entire end-to-end architecture. You have people looking into edge computing problems, into core network optimization, into resource allocation. But my work and my talk are focused on this last hop, which is the wireless hop of this network architecture. So the wireless connection between the headset and the radio access network. So what do we need if we want to cut this wire? So we have our headset, we want to remove the wire and want to wirelessly connect it to the backend, which can be an edge, a local computer or an edge server or a cloud server. On one hand, we need to have uplink connectivity to transmit spatial context about the user. This spatial context includes things like the current location of the user, which can change if the user can walk around, the rotation of their head, the gestures they are making with their hands, their posture, so how the body is positioned, which you require if you want to have a virtual avatar that's synchronized with your physical body, and also your gaze, where you are looking. All this information is needed to update the virtual world. Based on this update, we can then render the image that's viewed by the user and send back this content. This is the visual feed. Obviously, we also need to send back audio and haptic feedback if the user is wearing haptic gloves or even a full body haptic suit. So this is the information that we need to be able to transmit. However, there are some problems if we want to wirelessly transmit all this information. First one is that XR content streaming requires extremely high bandwidth. Currently, we are usually only doing 360 4K images, which are, if very heavily compressed, are about 15 to 20 megabits per second to transmit. This is doable with current network technologies such as Wi-Fi or 4G. However, if we want to increase the quality, which is for immersive virtual reality a requirement because you have a very large image as a user can look around everywhere, it very quickly the bandwidth explodes, the bandwidth requirements. If you want 16K 360 video, it's already up to 500 megabits per second. If you want to be able to show point cloud holograms, it's up to 2 gigabits per second. And if you want to go to future technologies like light fields, it can be terabits per second. So obviously, current network technologies like traditional Wi-Fi, even the new Wi-Fi standards like 802.11ax, are not really able to guarantee 2 gigabits per second per user if there are multiple users in the room. So this is a problem. A second issue is the latency. The latency requirements for virtual and augmented reality are extremely low. Here you see a video of a colleague of mine trying to catch a basketball with a headset on his head and the video image delayed for about 30 seconds. As you can see, he's not really able to catch the ball. This affects his immersion, as it's very hard to interact with the virtual world if there's a delay of even only 30 seconds. Second problem is that actually you get cyber sickness after a while with this delay. And now you can see him trying to catch the ball as well, but with a delay of only 2 milliseconds. And this is the target that we have for wireless VR. So as you can see, now he is able to catch the ball, which means that the interactions with the virtual world would be much more realistic and immersive. So the problem is that we need to combine very high data rates, gigabits per second, with very low latencies of maybe 1 or 2 milliseconds for the wireless part, because in general, they say that the total end-to-end latency should be around 10 milliseconds for interactive VR, but this includes obviously the processing and also transmission in the core network. So, and as you can see here in this graph, current 5G technology and Wi-Fi technology is not really able to provide such guarantees. While there are Wi-Fi standards like the mmWave Wi-Fi standard, which I will talk about in a second, which can guarantee very high data rates, they cannot guarantee low latencies, as the latency of Wi-Fi is not deterministic. On the other hand, 5G allows very low latencies, for example, with the URLC traffic class, ultra reliable low latency communications. However, this traffic class is created for very low data rates, for very small packet transmissions. And if you go to higher data rates, 100 megabits per second per user, then you can no longer guarantee this low latency. And 100 megabits per user is still not enough for future VR. So our goal is to develop network solutions that can combine this millisecond latency with this +1 gigabit per second data rate. For that, we need mmWave or sub-terahertz frequencies, because lower frequencies, traditional wireless frequencies below 6 gigahertz, just don't have enough bandwidth available to have such high data rates per user. So if we want to go for really high data rates, we need mmWave above 30 gigahertz. However, the problem with mmWave and terahertz is that there's very high path loss, which scales with the frequency squared. Also, in 60 gigahertz bands, the signals are absorbed by oxygen. So to overcome this high path loss, we need to use directional beams. So traditional networks are omnidirectional. You can receive the data no matter where you are in relation to the access point. With mmWave, you want to use directional beams to reduce the path loss. Moreover, it's more susceptible to blockage, such as other people walking in between the user and the access point, or a wall blocking the signal, and so on. So to overcome this, we need also beamforming, but also handovers or intelligent surfaces and so on. So we need a solution for these two problems. And here you can see a proposed architecture for wireless mmWave VR using high rate, low latency communication, or HRLC. So our user is connected wirelessly to the access point with a directional beam, which has to, of course, follow the user. So as the user moves their head or moves around, the beamforming needs to adapt to the new location of the user. Moreover, we need low latency channel access, which traditionally Wi-Fi does not necessarily provide, to be able to send the data really quickly with guarantees. Second problem, as I mentioned, are blocking obstacles. So if the signal is blocked, then we need to either perform a handover or use some kind of reconfigurable intelligent surface to redirect the signal. So as I said, another option is to do a handover to another access point and then send the signal from there. Today in my talk, I will focus on these two aspects here on the left. The other two aspects are left for future work. There are also other researchers who are already working on these topics. So let me start with the low latency channel access for mmWave Wi-Fi. So as I mentioned, traditionally Wi-Fi does not guarantee very low latencies in the order of a single millisecond or a few milliseconds. So in our work, we studied if the millimeter wave Wi-Fi standards would be able to guarantee low latencies. So there are actually two millimeter wave Wi-Fi standards. The first one that is already quite old, from 2012, is 802.11ad. And the newer one, which was standardized end of last year, is 802.11ay. Both of them use the same frequency band, so 57 to 71 gigahertz, with very wide channels with a lot of bandwidth, so more than 2 gigahertz per channel, which is much more than traditional Wi-Fi in the sub 6 gigahertz bands. Therefore, the data rates are also quite high. AD can theoretically achieve a data rate up to around 6 gigabits per second, while AY can go up to 44 gigabits per second per stream, and it can support up to 4 simultaneous streams using multi-user MIMO. So that's very high data rates. They both use beamforming to do this directional, to have these directional beams aimed towards the user. So it's sector-based, which means that the circle is split into separate sectors, and then the access point finds a sector that in which the user is currently located. There are different channel access methods. One is contention-based, called CBAP, and the other one is time slotted, called service periods, where you make reservations for time slots. In addition, the new standard has extended these channel access methods with support for multiple channels and MIMO. So that means channel bonding or aggregation, where you can combine multiple of these 6 channels into one bigger channel to have even higher data rate per user. The old standard also does not support any MIMO at all or channel bonding. However, our study focused on this AD standard. Maybe you wonder why. Well, it was because at the time when we did our study, there was no simulation framework available for AY, and also our code is quite easily extendable to the new features in AY, which are MIMO and multi-channel support. Most of the other aspects actually remain the same between the two standards. So here you see how channel access works in AD, but actually in AY it works very similarly. So the airtime is split, each beacon interval is split into two sub-time windows. The first one is the beacon header interval, where the beacon is transmitted, where beamforming training is done. So that means looking for the right sector for the access point to transmit to the user, and also for the user to listen to the access point, and also to send management traffic in this announcement transmission interval. Then you have the data transmission interval, which is here marked in dark blue, where you can have different periods. You can have contention-based periods where everyone can compete for the channel. So that's called CBAP. And you can have service periods where only a predefined sender can transmit to a predefined receiver. So this is reserved time slots. These time slots can be scheduled using regular service periods, or can be assigned just before the start using dynamic service periods, where a station actually requests one of these periods. The announcement of these periods is done, of course, in the beacon transmission. Within a CBAP, all the stations use EDCA, just like in regular Wi-Fi. So they have to listen, back off, and transmit. However, a problem to achieve very low latencies with this standard is already this beacon header interval, because during this entire period of time, no data transmissions can occur. So the duration of this beacon header interval already puts a minimum on the minimum achievable latency. So, and by default, if you use the default configuration, this is actually already 1.6 milliseconds. So that already means you would never be able to guarantee sub-millisecond or 1 millisecond latencies with this default configuration. So before we did our study, we also looked into what are the possibilities to optimize this further. And actually the ATI, this announcement transmission interval, is optional, so it can be disabled. Also, it's not needed to transmit beacons in every beacon interval. You can actually do it every 4 beacon intervals, but you have to do it in each of the sectors. So this is the minimum required. Also, the beamforming training does not need to be done every beacon interval. So if you don't expect too much mobility of the users, you can not do beacon forming training every beacon interval. And this can reduce the latency to 249 microseconds. Sorry, the time of this beacon header interval, which is already a lot better. Of course, the downside now is that we transmit less beacons, we do less beamforming training, so this might affect the performance under mobility, which is something we haven't studied yet. So then let's take a look at the overheads that occur during the data transmission interval, because there are some time periods where no transmission can occur. So during SABAP, you have slotting, which can take 0 to 5 microseconds, and you also have a backoff after transmitting data. You can actually perform this backoff already before your next packet is ready to be transmitted. So that's why you can do it after a transmission, and you can account for this latency after a transmission. In service period, you have a guard time, which has a variable length, and it changes with the beacon interval, duration, and so on, because it basically serves to avoid problems with clock drift and clock synchronization. In the paper on this topic, we described in detail how this guard time is calculated. And if you have a dynamic service period, you also need to request and approve a ground to transmit data. So this is also taking some time. So then we built a model taking into account all of these worst case latencies that can occur. And in the model, we also look at the specifics of VR video frame transmission, because this kind of traffic is a bit different than normal data transmissions, because you have basically bursty traffic. You have a transmission of a video frame, which is very big, especially if you look at 4K or even 16K or even higher definition video. So one of these video frames is much bigger than a single packet. This is many physical layer frames or many MAC layer packets. But there's a lot of downtime in between these packets. So that means that your video throughput is a lot smaller than your network throughput. If your network throughput is 6 gigabits per second, you will never be able to transmit live interactive VR content at 6 gigabits per second, because you have some downtime between frames. And for example, if you look at 60 frames per second, there is actually 17 milliseconds of downtime between frames. So this allows you to actually interleave the content of multiple users without any effect on the latency. As you can see here, we can transmit the frames of other users in this time where we are not transmitting video frames of user one. And we can accommodate for multiple users without affecting each other's latency if they are properly synchronized. And we considered also this synchronization, because by default, when you transmit video data over your wireless network, there's no synchronization. And the video frame transmissions of multiple users could overlap, which means that the data of one user will be delayed, causing additional latency. Moreover, if you don't have any coordination, the video frame transmission can overlap with this beacon header interval. And during this interval, no data can be transmitted, so then the video frame will also occur delays. So we also looked at the system where at least the transmission of the user video frames is coordinated. So we assume there is some kind of content server that generates the video data of all the users in the network, in the wireless network, and it coordinates that the frames are not generated at the same time to avoid this latency. Finally, we can also have network application coordination where we ensure that the frames are also not generated at the time the beacon header interval occurs. This, of course, is much more complicated and would require extremely low latency synchronization between your content server and your Wi-Fi access point, which is not so trivial to achieve. So the first case is the easiest to implement, while the third one is very complicated to implement in practice. Then we like I said, we built the model, we evaluated it for these different types of synchronization, and we evaluated for a scenario with multiple VR users in a room with a ceiling mounted access point, so assuming that there is no blockage between the access point and the users, and considering the specific traffic patterns of virtual reality. And our first goal was to check for specific latency bounds, what kind of data rate, VR per user data rate in megabits per second for 120 frames per second video could be achieved. And first here on the left, we look at full coordination. So coordination between the application and the access point. We looked at a single user and 8 user. HMD here stands for head-mounted display, which is the VR headset basically. Then we set a latency bounds. So this means that we allowed at most 1 millisecond latency of a full video frame transmission. So this is not the latency of a single data packet, but a full video frame. And this allowed us to achieve video data rates of about 500 megabits per second if we allowed 1 millisecond. If we allowed 5 milliseconds, which of course gives you more freedom, we are able to send a video of 2.5 gigabits per second per user for a single user. If you look at 8 users, there's a cap at 498 megabits per second. As you see, this is not much lower than for a single user at 1 millisecond because the video frames can be interleaved. In these cases, and also here in this case with only video coordination, so no coordination of the header transmission, the type of channel access you use has very little impact on the data rate. As you see, the data rate is always more or less the same in these cases. However, if we look at this case here, where we have one user, 1 millisecond latency, so very strict latency bounds, and only video coordination, we already see some differences in the achievable throughput. When we reserve time slots, the latency will actually suffer compared to doing contention-based channel access. And if we have 8 users, then actually and 1 millisecond latency bounds, then actually the service period approach is not useful, not working at all due to the high guard time that causes high latency. So this is more or less the conclusion from this theoretical model that service periods can have a very strong effect on the data rate that's achievable if you want to achieve very low latency. And in that case, actually contention-based, which is a bit counterintuitive, works better. We also validated our theoretical results with the NS3 simulator, where we used an existing module for 802.11 AD. And that's the reason why I said we used AD instead of AY for this study. Now, actually, they are working on an AY implementation for NS3. And here you can see cumulative distribution function of the latencies for all the different approaches with different latencies. And what's important to note is that here you see the latency bounds that while the distribution shows some long tails here, the worst case latency, so the 100% latency, is always below this latency bound that we set. This is, of course, an initial study where we didn't consider mobility of users and where we didn't consider obstacles, especially dynamic obstacles. This is something that could affect, of course, our worst case latency bound. So here we show that we can guarantee a worst case latency between 1 and 5 milliseconds under relatively perfect conditions. So that is the future work as well. We want to extend this to 802.11 AY features such as multi-user MIMO, channel bonding, new modulation schemes that are supported to see how much higher data rates we can achieve in those cases, but also to look at suboptimal channel conditions, blockage, mobility of users, and so on. What we've shown now is that for a single access point with up to 8 users, we can achieve 1 millisecond latency for 4K video content up to 400 megabits per second. However, for future applications where we want to have gigabits per second, we'll need the current Wi-Fi technology is not able to guarantee 1 millisecond latency, but can guarantee 5 milliseconds. So this was the first of the 2 main topics, namely channel access in millimeter wave Wi-Fi. For my second topic, I will look at the beamforming aspect, because as I mentioned, for millimeter wave, VR, we also need to do beamforming, and it needs to be done in real time because the VR user will rotate their head and will move around. So these are the characteristics of VR optimized beamforming. First of all, we have some additional information that we can use that is not available in a traditional millimeter wave network. Namely, we can use the spatial context information that's collected from the headset, such as where the user is looking, what's the position of the user, but we can also even collect eye movements, on-screen content, and so on, which we can use to predict how the user will move their head in the future. However, the beamforming must be very dynamic and done in real time, because here you see data that we actually collected with a real VR headset where a user was looking around, and you can achieve on a very short time scale, obviously, head rotations up to 900 degrees per second. In a VR millimeter wave scenario, the antenna will be positioned on top of the VR headset, so on top of the user's head. So if the user rotates their head, also the antenna will rotate, and we need to do receiver side beamforming, which needs to react very quickly to these very high rotational speeds. Obviously, over longer periods of time, like you see here on the yellow line, where we average the rotation over a full second, the rotations are slower. So that means the user will rotate very fast for a very short period of time. That means we need to adapt at very small time scales. So that probably means we need to adapt the beamforming between the transmission of every frame, video frame. So every 10 to 20 milliseconds. And the main challenge is the receiver side beamforming on the headset, because the movement, the lateral movements of the user, for example, when he's walking around, are much slower than the head rotations. So for the slower movements of the user, we need to do transmission side beamforming on the access point, obviously. But in this work, we looked at receiver side beamforming to address head rotation effects. So how do we do this? We first measure head rotations using onboard headset sensors data. So usually many headsets have, like the Oculus Quest that I mentioned before, they have onboard sensors to measure head rotations. We use these head rotations to predict what we expect will be the rotation of the user's head, and as a consequence, also the rotation of the antenna. And actually, we look at it from the point of view on the receiver antenna. So what we predict is the relative rotation of the access point compared to the receiver antenna over a small time window, between a few milliseconds and 100 milliseconds. And then we configure the receiver antenna subarray to cover this trajectory. So here you see an example of such a trajectory in UV coordinate space. And then what we do is we aim our antennas to cover with high SNR this path, this trajectory that we expect the user's head will move by in the next couple of milliseconds. So the direction of the access point from the headset will change quickly over time, as I mentioned. So the beam should cover this upcoming predicted direction for transmitting the next video frame. We need a dynamically shaped beam that follows this long trajectory. And this can be done by using virtual subarrays to form subbeams. So we form round beams across this trajectory, and together by doing phase synchronization of these subbeams, we can cover nicely this full trajectory. We consider a kind of antenna array, analog antenna array, like here in the picture. So with configurable subarrays. So here in the picture, all the antenna elements of the same color represent a single virtual subarray that will create a single beam that is directed at a certain part of the path which the headset rotation will follow. Then we split our entire antenna array into blocks. So these blocks are marked with the black lines. So within each block here in this example, we have 4 subarrays, 4 different ones. So we have 4x4 antenna subarrays. So we have 16 antennas, subarray antennas that we can point at different places. We also need some distance. Usually the distance between antenna elements is about half the wavelength, but because we are interleaving our antenna subarrays, we can reduce this to, in this case, 0.25 times the wavelength, which allows us to make a smaller antenna array, which is important for VR because you don't want the 20 diameter centimeter antenna array on top of your head. You want it to be a few centimeters at most, so it fits nicely within the form factor of your headset. And it's not as simple as you may think. So we developed an algorithm that actually, based on this predicted path that the headset will follow, will cover it with, will configure the antenna subarrays and will cover the path with as high as possible SNR. So we'll focus the energy of the transmission on this path. The problem is that there is a so-called aperture fusion effect. So if we have two subbeams that are pointed at the same location, and these subbeams together will increase the size or the aperture of our antenna array. And the beam width is inversely proportional with this aperture size. So the more beams we use and focus on the same point, the narrower the beams will become, and we will create this effects, namely holes where there's no coverage, where the SNR is bad, and where the reception is not good. This also occurs when these two beams are not pointed directly at the same place, but near each other, which occurs in our approach where we cover the entire path by pointing beams to adjacent locations. And here you see the effect that occurs if we have two subarrays from different blocks. So that means one from, for example, this first block and one from the second block, pointed at the same direction. And you see that then we create these holes, and it becomes different if they are vertically, if they're from horizontally adjacent blocks, vertically adjacent blocks, or diagonally adjacent blocks. If they are from the same block, this effect doesn't occur because the subbeams in the same block are interleaved. As you see here, they're interleaved. So by combining two of them, the total size does not become much bigger, only 0.25 times the wavelength. While if you combine the red one here with the green one here, our aperture size becomes much bigger, which causes the beams to change shape. So on one hand, this creates holes, which is bad for the reception quality of the signal. But on the other hand, it can also be exploited to influence the shape of our beams. And in our algorithm called coverage, we exploit this aperture fusion effect. So on one hand, we want to mitigate unwanted aperture fusion effects to avoid these holes in our path. And to do that, we between two blocks, so here you see two blocks in our antenna array, with each block having different subarrays in different colors. We actually remove one subarray in each block. So in this case, we remove A1, which is the red one, and B1, which is the blue one here. And we combine half of the elements of each of them into a new subarray called T1. We did the same for blocks A2 and B2, combining them in T2. And these other elements of A1 and of B1 are disabled, which can be done in many existing antenna arrays. And then we now have, of course, less subarrays. So that means we have less beams that we can point in the right direction. So this is a downside, but the upside is that by including these transitional subarrays, we can reduce the effect of aperture fusion. On top of that, the algorithm will exploit transitions from one subarray to another between blocks, which can be a horizontal transition, as you see here, or a vertical transition, as you see here. We'll exploit those to create a beam in the right, a path of beams in the right shape. And by doing a lot of vertical transitions, like here, between blocks, so each of these green dots represents a subarray, while the ones here in the middle represent transitional subarrays that we created. By doing a lot of vertical transitions, we can create a very tight signal with very high energy focused on the path directly. While if we reduce the number of transitions, either vertical or horizontal, we can create a wider path, a looser path, either a horizontal one, a semi-diagonal one, or a diagonal one. So what does our algorithm do exactly? Well, it decides based on the predicted shape of the path, whether it's horizontal, diagonal, semi-diagonal, vertical, whether it should be tight or loose. It decides how many of these transitional blocks to create, where to create them, and how many transitions between horizontal and vertical blocks to introduce. This is all done in real time. And here you can see some examples of a trajectory of the SNR of a trajectory that our algorithm, our coverage algorithm, has created with using this sub-beamforming. So here you see 3 example trajectories, and at the top you see loose beams, and at the bottom you see tighter beams where we exploit the aperture fusion effect to create tighter beams with more focus energy. Clearly, intuitively, a tighter beam is good if you can accurately predict the path that the headset will move at. However, if your prediction is not very accurate, then it's better to have a loose beam because it provides also good coverage in areas a bit further away from this predicted path. Let's say the real path is a little upwards, moved upwards, then with a loose beam, we still have good coverage. With a tight one, we end up in this darker blue region where the SNR is very bad and the coverage is therefore also bad and the signal would be bad. Here you see average results over 100,000 random trajectories. So there you can see that the tight trajectories give a better beamforming gain, slightly better beamforming gain than the loose ones. So the loose ones are the red line, tight ones are the blue line, for very short trajectories. Here we are assuming that the prediction is 100% accurate as well, which in reality may not always be the case. As a trajectory then becomes longer, the loose one gives a better fit, gives a better result, especially if you look at the confidence intervals, where the blue one has some very strong outliers with very low beamforming gain. Obviously, also as a trajectory becomes longer, it becomes harder to fit, to actually cover the entire path with sub-beams because the number of sub-beams are limited. So what we want to do is do an update quite frequently so that our trajectories of head movements do not become too long. We also tested this for trajectories with prediction errors. So we predict our trajectory, but then the real trajectory is not exactly the same. And here you see basically that then a loose beam is always better than a tight one, because obviously the tight beam is very focused on the predicted trajectory. So if this is not correct, the prediction, then it gives very poor signal quality. And here you see that these dotted lines represent off trajectory, so that predictions and the prediction errors become bigger and bigger. But even in the worst case, with very strong, very big errors in prediction, the red line, which is the loose trajectory, still performs relatively okay, especially compared to the blue line here, which has a very low gain. So that's the coverage algorithm, which calculates in real time the receiver side beamforming configuration of your antenna array based on predictions of how your head will rotate in the near future. We're also looking into how we can predict these head rotations, because in coverage, in the coverage work, we just assume the prediction is available, either with an error or without. But we are also interested to see how big are these errors in reality. So we have done some initial experiments, and this is very early work. It's work in progress to look at the accuracy of the sensor data collected from a head-mounted display. So how accurately can we measure rotations of the user's head with a head-mounted display? So the question is this prediction enough for coverage, for our coverage algorithm? And there are some existing analysis of these headset sensors in literature, but they didn't check during rotation, only during rest, before or after rotation, and so on. So we are interested to see how accurate are the sensors while the headset is rotating. To measure this, we need some ground truth, and the ground truth we got from a robot arm, which also allows us to create repeatability, because we can program this robot arm, and this robot arm is very accurate. We can very accurately measure the angles that it's holding the headset in. And we can also repeat the same experiment many times, because we can just program the robot arm and it will repeat the same actions over and over. So here you see some pictures of our experiments where we put a Oculus Quest headset on one of these robot arms. Then we programmed the robot arm to do certain movements in different speeds. So here you see one example, well, two examples of two trajectories that we programmed. And then we compared the angles measured by the robot arm with those measured by the VR headset. We had to do some data analytics and transformation, because the robot arm measures at 125 Hertz. So it reports 125 times per second, a new measurement of the angular velocity. Well, the headset does this in theory 1000 times per second, but in practice it was more 987 times per second. So it was not always the same. Then we processed the data and we compared the angular velocity of our robot arm, which is the orange line, which we assume to be perfectly accurate. Obviously, in reality, there's a very small error here, but this error is negligible. Our headset clearly follows exactly the same rotations, but with some error. However, the error is, it looks big here, but it's actually very small, because here the angular velocity in this peak is about 0.7 radians per second, while the headset measured 0.775. So an error of 0.075 radians per second, which is not so high, and actually is probably good enough for using it as a predictor for our coverage algorithm. And that brings me to the conclusion of my talk. So today I talked about mmWave technology and whether or not it is suitable for real-time interactive virtual reality with mobile users. We focus mainly on low latency channel access, where we studied channel access for mmWave Wi-Fi standards, and we checked if they are able to transmit video frames for VR at latencies between 1 and 5 milliseconds. Here we showed that AD is sufficient for 4K VR, but probably we need a new AY standard for higher resolution virtual reality. We also looked at beamforming at the user side. So there I presented the coverage algorithm, which is able to optimize beamforming for head rotations. Obviously, this needs a strategy for predicting these head rotations, for which we are studying the accuracy of the onboard sensors of VR headsets. The other aspects, such as handovers, reconfigurable intelligent surfaces, and doing transmit side beamforming, are left for future work. And finally, let me end here with showing you the sources of the research that I used as a basis for this presentation. Thank you very much for your attention, and feel free to ask your questions.
Thank you for your presentation. We have several questions in chat.
Okay, let me take a look. So slide 26 is the first question. The question is it about downlink transmission? Yes, this is about pure downlink. So here we don't look at the uplink of the sensor data or audio or haptic feeds. We only look at the video feed. So obviously this work could be extended to also include the uplink transmission, which is much lower data rate. The sensor data is not gigabits per second, but this could be included in the future, yes. Second question, slide 31. What is UV space? Is it more convenient for use for orientation of the user's head than traditional angles? Yes, actually, it's the good thing about using UV space for this is that, and this is actually something we explain in the paper, that these sub beams are nicely round in UV space, while they are stretched out if you look at other like Euclidean space, for example. So that's why we transform everything into UV space. So there's no, you could also do the calculations in another space, but UV space is actually best suited and easiest to represent visually the data. Don't know if there are other questions.
I have some questions and comments. It's Evgeny. So related to slide 26. So yes. I think that, there is no surprise that you obtained such results, because if you have only downlink transmission, you don't have any contention. And so that's why you don't need to do any reservation with service periods. So
yeah, that is true. And in this case, the overhead of the service periods indeed has a big effect, because there's not the downside of contention. What could also be looked at is combining service periods for uplink data with contention-based downlink transmissions, for example. But that's, like I said, something for future work that we haven't looked into yet.
But if you don't have a lot of devices, it seems that there will not be any impact, any huge impacts at least. So you can use contention-based access periods without any issues.
That is true. Yes.
Okay. And also, I have a comment related to slide 15.
Mm-hmm.
So here you mentioned that Wi-Fi has so huge delays, latencies. How did you measure? How did you obtain such huge latencies? Because typically in Wi-Fi, if the network is not overloaded, the delays are around 1 millisecond.
Yes, that's true. This data comes from literature, and it's what they were aiming at, I believe, is that in Wi-Fi you have no guarantees concerning latency. And as I showed in the other results, with your default configuration of, for example, your beacon header interval, your beamforming training, you will add additional latencies that will increase your latency to more than 1 millisecond. On top of that, you can have contention, which can cause higher latencies, especially in denser networks. So that's why I guess they mentioned here that Wi-Fi has a higher latency, while I would say in reality, maybe it would be better to show it as a bigger circle that goes from 1 millisecond up to 100, depending on the circumstances. It's very hard to say anything about the latency of traditional Wi-Fi, I would say, because it depends very much on your scenario and your network conditions.
Yeah, sure. And as for 5G latency, so if you consider like current 5G deployments, the latency is typically above 1 millisecond. Because standard, there is a lot of interesting things in the standard, but they're not implemented yet.
Yes, I think most of deployments now are more the mmWave traffic class, which is around 10 or more milliseconds indeed. 4G is around 30. In practice, we did some measurements with 4G, and there you are even at 30 milliseconds or higher. But yeah, in theory, the URLC class is able to go below 1 millisecond, but I'm not sure if there's actually any real deployments of that at the moment.
And also, actually, thank you very much for this very interesting presentation and talk. And I like very much your study on millimeter wave Wi-Fi is excellent. But at the beginning, you mentioned something about Hertz communications. And I have a question. So do you believe that Hertz communications can really improve, can really boost the performance for VR?
So you mentioned, what did you say? What kind of communication?
Terahertz. It was somewhere in the beginning.
Yes, I mentioned millimeter wave and above. I'm maybe more sub-terahertz. So between 30 and 300 gigahertz is what I'm mainly talking about. Actually, in the study on the beamforming that we did, we looked at 140 gigahertz, not at 60 gigahertz, because the advantage of these higher frequencies is, on one hand, the higher data rate, but on the other hand, also your antenna array becomes smaller, so you can have a bigger antenna array, which also improves your beamforming performance. So I don't think actual terahertz above 1 terahertz is usable for VR because the distances are just too short. I do think 140 gigahertz and maybe 300 gigahertz might be feasible for example, room-based deployments in a single room.
Also, a question: did you consider similar scenario, the performance of AX or even BE.11be, which shall provide much higher data rates, but it doesn't have such issues related to the requirement of very narrow beams and so far?
Yes, well, the problem with AX is that it can guarantee a few gigabits per second, I think. But if you have more users, then it no longer provides enough data rates. Another reason we look at mmWave is because in AX and BE, you're using the 2.4 and 5 gigahertz bands, which are very prone to interference. So, and then you have no more control over the latency. And then you will get latency peaks, which are very bad for the user experience in VR. So latency is very important. In mmWave, you have the beamforming, that is true. But on the other hand, because you have these directed beams, you have also much lower chance of having interference. So you have much more control over the latency. But we didn't test it. So actually, some of my colleagues are working on AX and BE. And they are looking at ultra low latency communication with AX, so wireless time sensitive networking, but they look at industrial applications with low data rates. And
okay, maybe my final question. It's actually not a question, it's a remark. So on your slide with .11ay properties,
yes,
I have a question. Why did you mention the data rate in .11ay is 44 gigabit per second? So how you obtain this figure?
This number is also, I got it from a paper, from literature.
Okay, because as far as I remember, so the data rate in .11ay is 8 gigabit per second for each 2 gigahertz band, 2 gigahertz channel. So, and if we have 8 gigahertz channel, so it shall be multiplied by 4, and actually the number of spatial streams shall be 8. So the data rate is something about 270, as I remember. So that's what my question. So I don't remember exactly, but I have some doubts about just this figure.
Yeah, I don't know exact numbers by heart, but I think it's that it's around 8 per channel, but I think they assume 6 channels, not 8. So
8.
Then you have
the standard allows 8, as far as I remember. Oh,
yeah.
Sorry, 4 channels can be aggregated together, and each channel may have 8 spatial streams.
Yeah, I don't know where the figure came from, because also they say there are 6 frequency bands, so 6 channels. I guess it depends maybe which part of the world and how.
No. A 6 channel is the available bandwidth.
Yes, but you can aggregate these
only 4
together.
Only 4. Yeah.
I don't know where they got the number from, so I didn't really check it. I just read in a paper and I cited it. So maybe it's not 100% correct.
Don't worry. Just I thought you made some calculations. So this is like real data rate. No. Okay. So thank you very much. That's all from my side, and I hope my colleagues will ask more questions. Thank you.
Thank you, Evgeny.
It was really very interesting.
Thank you for the feedback as well. Any other questions?
Yes, my question is about results on slide 26.
Mm-hmm.
So, as I understand, you have problems when you have several head-mounted devices connected to a single access point. So my question is, what is exactly the sector size in the .11ad and .11ay? So maybe the solution of this problem is just to have multiple access points and one per each HMD.
So I think we assumed here 8 sectors, which is also what a off-the-shelf AD access point that we tested supports. And indeed, by adding more access points, you can create spatial diversity and support more users. Obviously, in practice, you want to minimize the number of access points because they're very expensive and you want to have as few as possible for your setup. So if you can have more users per access point, that is better. But as you say, if you look at it purely from a research point of view, more access points would indeed allow you to increase the data rate if you avoid the interference by creating narrow enough beams. I would say that is a possibility.
Because I believe that this is possible solution also because this is head-mounted devices and they cannot be located closely because they are on the heads of the people. So thank you for this comment and answer. And my second question is about results presented in the second section of your talk. And you mentioned that in the first section, you validate your results using NS3 simulation. In the third part, you validate by using robots. And which type of validation do you use in the second part? Because maybe I missed it.
I forgot to mention that here we use basically a MATLAB model for beamforming in mmWave. So just a mathematical formula. So we haven't validated this with real hardware. This is something we want to do, but it's not easy to get your hands on mmWave hardware where it's actually the beamforming is fully configurable. So that's the reason we use the theoretical model.
And on some of the previous slides, you show the speed of movement of the head. So
yes. This is real data. This is with the headset. So the same headset that you saw in the last part of the presentation with the robot arm. Here we just put the headset on someone's head. We gave them some video, some VR content, and then we just measured the head rotation speed with the sensors that are on board. So this is real data that we then input in the simulation.
Thank you.
My pleasure. Other questions?
Yeah, well, thank you for your talk. It's Michael speaking. I wanted to ask you about the second part of the talk too. Did you, in the last slides, you mentioned that you, with experiments with the robotic hand, you obtain the results saying that, Oculus headset has some errors in measuring the degrees and the rotational speed, etc. And I wonder if you tried to simulate these errors back into the original, into your model, so to check.
Not yet, because these are the errors in the measurements, but what the coverage algorithm expects is not just the measurement, but also a prediction of the short-term future. So we would need to combine these measurements with a predictor, like a very low, for example, regression predictor or something, low overhead predictor. But we haven't had the time to do this yet. So this is work in progress, actually. It would indeed be interesting to feed this back into the simulation, because now in the simulation here, we considered like fixed errors, like artificial errors, and we introduced. We didn't consider the real error. So that would be a next step to once we have a predictor for head rotations, to feed that back into this algorithm.
Yeah, okay. And maybe since you mentioned the predictions, so and now you used these predictions as they are provided by the headset or something like that.
Yeah, so this is receiver side beamforming, so on the headset. So we assume that we have the predictions done on the headset locally, which is realistic because the headset has the sensors usually on board, especially modern headsets. In the past, you usually had to use like an external system that measured the location and head rotation of the user. And then this was sent to the computer where the data was gathered, but modern headsets usually have all these sensors on board.
Yeah, okay. Thank you.
My pleasure.
Okay, I also have a question. Can you hear me?
Yes, go ahead.
First of all, thank you for a very interesting presentation. My question is exactly about the slide which is on the screen. Maybe I missed that, but you have here figures. And on the x-axis, you have UV space trajectory length. So does really this beamforming gain depend on the exact trajectory, how it looks like, or it only depends on the length?
It also depends on the actual trajectory itself. Some are easier to cover than others. You can see this in the shaded areas because those are the confidence intervals. So the lines show the average here on the left graph, but the shaded areas show the 98%, 99.8%, and 100% confidence intervals. So there you can actually see that there are some outliers. So there's a few trajectories, like less than 1%, I would say, or 2% that have very bad behavior, very bad results.
How did you generate these trajectories? Are they random or?
These are fully random. So these are 3 examples that are part of the set. So we just randomly generated 100,000 of these that we then tested on.
So they are not modeled like real behavior of players of some game. They are just random, right?
Yeah, but because we have evaluated so many, we think that they covered all the possibilities. So that's what we wanted to achieve here. We did do this test in the beginning with the head rotation speed, where we also looked at the trajectory, and trajectories look more or less like this if you look at the short time scale, because if you look at the longer time scale, the user will turn their head from one side to the other and then turn back, and then it will not be a nice straight line like here, but on short enough time scale it always looks like this.
And one more question is I think that this beamforming gain is very much depends on the channel model you use, because if you have, for example, your line of sight path is not so strong, and you have different walls and different non-line of sight paths that are strong enough to affect your performance, then you'll have degradation. Or you considered so the main question is what channel model was used?
Well, we actually looked at a simplified model, for which we evaluated most of the results, and then we also looked at a multi-path model with reflections to do a validation, but we didn't use that for all the results because it takes a lot of time to calculate. And the validation actually showed that the results are not so different. What we did not consider is blockage of the line of sight. We assume that in case there's a blockage, you will want to do a handover or something anyway. So here we just wanted to see how to optimally configure the receiver beamforming without really looking at the channel conditions, because no matter if the channel conditions are bad, there's a blockage, then every approach is going to be, or every solution is going to be bad. But we did look at reflections and such. And in the paper, we show results on that as well.
So am I right that you just consider path loss and the phase shift on different antennas?
Yes.
Okay. And did you compare these results, or maybe you have some ideas on how channel model really looks like in real environments where players now play different games? Are there the channel conditions really close to what you considered, or reflections should be considered as well, and it will change somehow the results?
Well, what we saw is that the reflections don't have a big influence, but what I cannot say is how it would be if there would be multiple users in the room and how that would affect the signal. So that is something we haven't checked, so I cannot really answer that. I think it might be that, I think it would be a good idea actually for a research topic to study actual path loss and channel models for VR environments, like a room with multiple users, with walls, maybe some objects. So it would be an interesting thing to check, but I cannot really answer that question right now because we didn't check this.
Thank you very much.
Thank you. Other questions?
Hello. I wanted to ask one question. So you were showing those lattices with the antennas, and could you please repeat, were they on a receiver or on a transmitter side?
These are receiver side antennas.
Mm-hmm. Okay, so and after that you were showing that you were somehow connecting some of these antennas together, and as I understood, you were not using all the antennas, is that right?
Yeah, it depends. Yeah, if we create, so let me show here in the example. So we create these transitional subarrays, virtual subarrays, and if we want to create these, which is done in this approach that you see here, we need to disable some antenna elements. And then, yeah, some antenna elements need to be disabled.
Well, that is interesting. I always thought that the more antennas you have, it is always the better. You just need to find some phase shifts to improve the reception beamforming. So you say that it is not always the case, right?
Yeah, because we combine these antennas in antenna elements, sorry, into a subarray, and all the subarrays we want them to be the same size. So then we have some elements left here. Yeah, these four, for example, here in this example, the subarray is 8 elements, 2 by 4. So then they cannot be part of a 2 by 4 subarray. So that's why we disable them. But it does affect performance to some extent by disabling elements. But by adding these transitional elements, virtual elements, we do create a bigger positive effect than the negative effect from disabling some of them.
Mm-hmm. Okay, I see. Thank you very much.
Thank you. Any other questions? So if anyone is interested in knowing more about this, here I also cite the papers where we discuss this in much more technical detail. The work on the beamforming is still in progress, so we haven't published anything officially, but there's an early version available on arXiv if you're interested.
So I guess that's all for today. Let us thank Professor Famaey for interesting talk. Also, I want to thank all participants of the seminar for joining our seminar and asking the question, because I believe we have very productive discussion today and interesting discussion. The next seminar will be held at November 12th. At this seminar, Victor Tagunakal will tell us about IEEE.11bd, which is a new amendment for Wi-Fi and at V2X scenarios. See you. Goodbye.
Thank you very much. Bye.